5.1 primitives of irrational functions. Okay, and I would like to discuss a little bit what is main goal of those sections about primitives. In fact, the material which is included into those sections, I mean, how to find primitives, it is rather complicated, right? And I would say you should know practically how to do it. That's the main point, right? And you see that I didn't give any example for integration of rational functions, I mean practical example. You should do it on seminars and by yourself. What I do here, I am explaining the theory which lies behind and why you can apply those methods. In fact, I am not going to ask you to repeat this during exam. That's quite different from proofs of theorems which were in the first semester and which will be after these indefinite integral topics. So, in fact, sorry, I should address to everybody, not only to you. Yeah. So, this material is to give you a background of seminars methods, nothing else. You don't need to know all those methods just to be able to repeat what I am doing here. No, not necessary. I will not ask it. Yeah? So, today's section is devoted to rational functions of special variables like u, v, maybe more, right? Where u, v are roots of polynomials of x. So R is a rational function, polynomial over polynomial. So we are talking about functions which contain some roots. And in general, many of those functions cannot be integrated in terms of elementary functions, unfortunately. But there are few particular cases when we can do it. So, the first case, okay, which letters I used? R of x, alpha x plus beta, gamma x plus delta, power R, where R is a rational number. And if R can be represented as a ratio with integer and natural, then we can find a primitive, we can find indefinite integral of that form. How? How? Very simple idea. So we can integrate it by substitution. By substitution. Very natural substitution, in fact. Namely, alpha x plus beta over gamma x plus delta equals to, let's say, t to the power n, where n is denominator of our rational. Okay. How it can help? Look, what is x? Let's express x from this expression. Alpha x plus beta equals t to the power n times gamma x plus delta. Then we can collect all terms with x in the left hand side, all terms without x in the right hand side, and after that we obtain such a relatively simple expression for x. Yeah. Alpha, beta, gamma are constants. I forget to mention it. Sorry. Alpha, beta, gamma, delta are real numbers. Of course, it makes a sense only when this ratio is indeed a rational function, but not a linear function and not a constant, better to say. Linear function is okay, but constant makes no sense. So, x is here. Now we can find dx. So we take derivative of numerator. It gives n times t to the power n minus 1 delta times denominator minus numerator times derivative of denominator. Minus n t to the power n minus 1 gamma over alpha minus t to the power n gamma squared times dt. And we can simplify a little bit because delta gamma terms will be cancelled. Delta gamma t to the power 2n minus 1, n with minus and here with plus. So those two terms are cancelled, and what remains? T to the power n minus 1 n times t to the power n minus 1 times alpha delta minus beta gamma. And in fact, I said we should consider only cases when this is not a constant and this is not a constant, precisely when alpha delta minus beta gamma is not 0. That is precisely the case when this ratio is not an identically constant. That is precisely the case when we don't need to do anything, right? Because if this is a constant, then this is just integral of a rational function. Nothing to do. Okay, so now everything is ready to make a substitution. And let us substitute what we have then. R of x alpha x plus beta over gamma x plus delta power r dx equals to, so look what we'll obtain. Here I should substitute this expression, t to the power n delta minus beta over alpha minus t to the power n gamma. And that one, what it will be? Look, t to the power n, power r is m over n, so we have just t to the power n. So this expression is a rational function of t. Just polynomials, and we substitute those expressions, we obtain rational functions. So after transformations, it will be a rational function of t. What remains? Let's write n minus 1 alpha delta minus beta gamma over alpha minus t to the power n gamma squared dt. And that is an integral of a rational function. So we know how to find those integrals. No need to. How I obtain dx. Once again, I took derivative of this expression, right? What is derivative of ratio? Derivative of numerator times denominator minus derivative of derivative of denominator times numerator. Okay. So you see, in this case, we can transform our integral with the help of a suitable substitution to another integral of a rational function, and we know from former section how to integrate arbitrary rational function. So we can find an integral in terms of t, and at the very end, look, we should substitute t equals to nth root of this ratio, right? So the answer will be a function of nth root of this ratio, right? Okay, elementary function. Next is integral of the following type, and in fact there are several different methods. So we consider a rational function of this form. ABC are real numbers. Of course, a is not equal to 0, otherwise it's easy to compute just by substitution bx plus c replaced by t squared, and after that it's easy to compute. Okay. But in principle, okay. So there are quite different methods to compute those integrals. And I'll start with so-called Euler substitutions. Euler substitutions. Euler's substitutions. What they are? there are several of them. So, first class of substitutions, not just one. It works when A is positive. If A is positive, then we make the following substitution. Plus or minus square root of ax plus or minus t. So, let me explain what means substitution here. Look, we had a variable x, right? Now there is a new variable t. And what is written here? I wrote an expression for both x and t, right? So both x and t are connected. You can choose any combination of signs, plus or minus. So in principle, here I wrote 4 different substitutions, right? And you can choose any of them, in fact. Unfortunately, no precise receipt what to choose, no. Because, in fact, I'll show now that any of those substitutions give you an integral of a rational function. But what is bad side of Euler substitution? Rational function in general is very huge. That is why, so sometimes you can feel somehow which combination of signs gives you a simpler rational function after the transformations. But of course, in fact, I would say in very few cases Euler substitutions give simple rational functions. Unfortunately, in most cases, they are huge. But in principle, it can be solved using Euler substitution. How? Look, take a square. So in fact, the main point, we are talking about integral r of x square root of ax squared plus bx plus c dx, right? And when we make a substitution, what we should do? We should know the expression for x, because if you know expression of x, substitute, and we have expression for square root also, right? And after that, if we have expression for x, we can find differential, right? To compute dx. So the task is to find an expression for x. How? Take a square of both sides. What we obtain after squaring? We have the following. Take square of this, ax squared plus or minus 2 square root of axt plus t squared. So here, plus or minus is determined by what? Either we choose equal signs or different, right? If they are equal, then we have plus here. If they are different, we have minus. That is how to choose plus or minus here. After that, look what is important. We can cancel. And that is the main idea which lies behind the substitution. After squaring, we cancel terms with x squared, right? And after that, what we can do, we can express x easily. Look, x times b minus plus 2 square root of at equals to t squared minus c. So we have an expression for for x. And after that we can find differential. Just take derivative of numerator 2t times b minus plus 2 square root of a t minus t squared minus t times derivative here is minus plus, so plus minus 2 square root of a over b minus plus 2 square root of a t dt. And in fact, you see that we can cancel a little bit. Plus minus t squared minus plus t squared. No. We have 4, 2. It is not cancelled, unfortunately. Okay, in fact, I think I can stop here, because now you see we can also substitute square root ax squared plus bx plus c equals to plus or minus square root of a times this x, t squared minus c, b minus plus 2 square root of a t, plus or minus t. And you see, after that, we should substitute all those three expressions into our integral. And it gives, after transformations, an integral of a rational function of t. And t, what is t? T can be found from this equality, obviously, right? So back substitution is easy. Of course, squared. Thank you. Yeah, squared, of course. Thanks. Thanks. Yeah, it was misprint. Thank you. Okay. Now, next, second Euler substitution works for C positive. So if C is positive, then the substitution is the following. Square root of ax squared plus bx plus c equals to plus or minus xt plus or minus square root of c. Once again, the main point is to express x as a function of t. What we should do, we take square of both sides. What we obtain, ax squared plus bx plus c equals to x squared t squared plus or minus 2 square root of cxt plus c. And again, main point here is we cancel c, and after that we can cancel common multiplier x in both sides. And it gives ax plus b equals to xt squared plus or minus 2 square root of ct. And you see only first degrees of x appear, no larger degrees, and we can express x. So x times a minus t squared equals to minus b plus or minus 2 square root of ct. X equals to minus b plus or minus 2 square root of ct over a minus t squared. That is an expression for x. So we can find dx, and that is minus b, firstly derivative of numerator gives here plus or minus 2 square root of ct times denominator a minus t squared minus numerator times derivative of denominator over square of denominator times dt. I think again we cannot cancel anything here. And square root of ax squared plus bx plus c equals to, we should substitute, plus minus t times minus b plus minus 2 square root of ct over a minus t squared plus or minus square root of c. So you see, in principle, once again, if we substitute all those three expressions into our integral, we'll obtain an integral of a rational function. Yeah. Okay. And the third substitution works when the expression on the square root is a polynomial with real zeros. So if ax squared plus bx plus c has two real zeros, right? So the third Euler substitution works in the case when we have two real zeros of the quadratic polynomial under square root. Then the substitution is as follows: plus or minus x minus x1 times t. Okay, once again, the main task in Euler substitution is to express x as a function of t, to be able to realize the substitution. So take square, and remember, the expression is this one. So I want to replace it, right? So I take square, it gives precisely ax squared plus bx plus c, and there is this expression. So here we have x minus x1 squared times t squared. And you see what we can do. We can cancel one term x minus x1. And after that, again, we have a linear polynomial in x. So we can express x. So x times a minus t squared equals to ax2 minus x1 t squared. So we have x equals to ax2 minus x1 t squared over a minus t squared. And we can find dx once again. So derivative of numerator minus 2x1t times a minus t squared minus derivative of denominator 2t times ax2 minus x1 t squared over a minus t squared squared dt, and square root of ax squared plus bx plus c will be plus or minus ax2 minus x1 t squared over a minus t squared minus x1 t. So you see, once again, if we substitute all those expressions, oh, by the way, here we can cancel leading powers of t, but it is not so important. So Once again, after substituting, we will obtain an integral of a rational function. But it will be rather huge rational function, unfortunately. Okay, these are earlier substitutions. As I said, those substitutions give you an integral of a rational function, so you can find an answer in principle. Any of them gives you an answer. Moreover, you see that, for example, imagine both A, C are positive and the polynomial has 2 real roots. It means that you can apply all 3 of those earlier substitutions, right? Each of them works. Which of them to choose? So the choice is enormous. And 4 choices in each of those cases, 2 choices over there, right? So many different choices. And okay, what is different? What is difference? Different rational functions. Some of them may be a little bit simpler, but in general, all of them are rather huge. And because of this, I mean, for the differential of the second substitution, derivative of denominator be minus 2t, not minus 2t squared. Second substitution. Oh, yeah. Thank you. Right. Just a minute. And also here I made a mistake. Oh, so many mistakes. Here and there, right? Derivative of numerator, that one. Derivative of denominator is that one. Okay. Yeah. Thank you. And yeah, but again, we cannot cancel anything. Is it okay here? Here it's okay. Okay, thank you. Yeah. So, you see that at the moment we have a method to compute arbitrary integral of this form, right? But there is a different method to compute at least part of those integrals. So, other methods. And I'll erase. So, other methods to compute. Once again, we have the same expression, but now we have slightly different idea to compute them. So, let me make such a notation. Denote capital Y as our quadratic polynomial, sorry. And small y is square root of capital Y. Now, what is rational function of x, y? Look, what is it? That is a polynomial of both variables x and y over another polynomial of variables x and y. So polynomials of two variables means you should take some powers of x, some powers of y, and multiply them, sum of them, and add the results with some coefficients. That is a polynomial, right? Now imagine you have different powers of x and y, right? Once you get y squared, what is y squared? Y squared. This one, right? So it means once you have y squared, you can express it as a polynomial of x, right? So y cubed, what is y cubed? Y squared times y. So it means polynomial of x times y. So as a result, we can write it as p1 of x plus y times p2 of x over q1 of x plus y times q2 of x. After that, what we can do? Remember, here we have square root, right? And there is so-called algebraic conjugate. So we can multiply by a difference here, right? We can multiply the ratio by difference here. So I can write like p1 of x plus y p2 of x times q1 of x minus y q2 of x over q1 squared of x minus y squared q2 squared of x. So now what we have in denominator is a polynomial of x, because y squared is again polynomial, right? So as a result, we have an expression of the following form: p of x plus y q of x over, let's say, r of x. So you see that arbitrary rational function of our variables x and y can be expressed in that form. So once you represent the function in that form, so you see, we want to integrate such an expression, right? First is a rational function. So nothing new is here, right? So what remains is to compute, to be able to compute an integral of, okay, now it will be a different, let's say r1 of x times y dx. r1 is a rational function now. And moreover, it is more convenient to represent it as, so put square root into the denominator, because little y is square root of capital Y, right? So it means we can easily put square root into denominator. It turns out that it is more convenient. So we have a rational function over y. And okay, there are general methods. Once we have a rational function, we know about partial fraction decomposition, right? First of all, we need to obtain a proper rational function, right? And after that, to write partial fraction decomposition. So there are methods to compute such an integral for any concrete partial fraction which appears in partial fraction decomposition. But I don't want to consider them. They are rather complicated. So let's skip them. But what I want to consider is, remember, so when you have rational function, the first step of what you should do is to divide, represent it as a polynomial plus a proper rational function. So I'll consider only the very first term, polynomial over y. So instead of this, I'll consider only particular case, polynomial over y. Only this one. P is a polynomial of degree m. Is a polynomial of degree m. And how to compute this? The main idea is some kind of indefinite coefficients, but for slightly different form. So, what is here? Q is a polynomial with arbitrary coefficients. And degree of Q equals to degree of P minus 1. Lambda is a constant. So, you see, that is something similar to what you should do to find partial fraction decomposition. So, I gave you general theorem that arbitrary rational function arbitrary proper rational function can be represented with the help of partial fraction decomposition, right? So I didn't give you a method how to find those coefficients. You just need to make a common denominator and compare coefficients in arbitrary degrees of x, and you will obtain a system of linear equations. And here we have slightly different story. So you see, polynomial with arbitrary coefficients. So if degree of P is m, then how many coefficients we have in Q? Look, degree of P is m. So degree of Q is m minus 1. Arbitrary polynomial of degree m minus 1 has how many coefficients? Look, polynomial of degree 2 has how many coefficients? How many coefficients has a polynomial of degree 2? 3 coefficients, right? So polynomial of degree m minus 1 has m coefficients. Plus 1, right? M coefficients. So you see here in Q we have m arbitrary coefficients, m plus 1. So altogether m plus 1 coefficients. How to find them? Just take a derivative of this expression. Look what we'll obtain. Derivative of integral is the function under integral. We know this property. P of x over y equals to, now let's compute here. That is q prime of x times y plus, now I should write what is y prime. Look, q of x y square root of capital Y. So derivative of square root is 1 over 2 square root of capital Y, so little y, right? Times derivative of capital Y. And derivative of capital Y is 2ax plus b. Plus derivative of the last term is lambda over y. So altogether, let me rewrite, take a common denominator, y in the right hand side, and compare numerators. So we have q prime of x capital Y, y squared here, plus q of x times ax plus b over 2 plus lambda. So I take common denominator little y. Lambda is a real number, yeah, of course, real. In fact, yeah, that is unknown real number. So you see, q is polynomial of degree m minus 1. We multiply it by a linear polynomial, so we have polynomial of degree m here, right? Over there, q prime, derivative of a polynomial of degree m minus 1 is a polynomial of degree m minus 2, right? Degree m minus 2, capital Y is a polynomial of degree 2. Altogether, again, polynomial of degree m. So polynomial of degree m is in the right-hand side, and polynomial of degree m is in the left-hand side. Altogether, we have m plus 1 equations, linear equations, in fact, to find unknown coefficients of polynomial q and lambda. Of course, I should prove that indeed that system has a unique solution, but I'll skip it. Okay? So, in fact, what I recommend to know in practice, to compute integrals on that form. So, you should know about Euler substitution, that they exist, right? But I recommend you to try to represent it in that form. And if it has this form, then it is essentially easier to apply this this version of method of indeterminate coefficients. Okay? Okay. Now there is a special, so fourth case, differential binomial. That is an integral of the following form. Here, m and p are rational numbers, a, b are real numbers. That is a differential binomial. Okay. In fact, there are only 3 cases when we can find this we can find a primitive for these irrational functions, for this irrational function in terms of elementary functions. So the first case when we can do it is if p is an integer. If p is an integer, then look, we can make a substitution x equals to t to the power lambda, where lambda is a common denominator in fact least common denominator, but not necessarily. Of course, the best would be to choose least common denominator of mn. So, why it works? Look, x equals to t to the power lambda. So it means m equals to, let's say, mu over lambda, n equals to nu over lambda, where mu are integers, lambda is natural. So we have a common denominator, right? A common denominator. What will happen then if we substitute? Look, what is x to the power m? That is x 1 over lambda power mu, or t to the power mu, right? Analogously, x to the power n equals to t to the power nu, and what we'll obtain, also dx. dx equals to lambda times t to the power lambda minus 1 dt. And if we substitute everything, what we'll obtain? Our integral, okay, like that, let me write. So t to the power mu times a t to the power nu plus b power p times lambda t to the power lambda minus 1 dt. Here, mu, nu, p, and lambda are integers. Now, it means this function is a rational function. So we can compute this integral by our methods from former section, right? So it works. Okay. Next is so to obtain other possible cases. So this case is over. Okay? So it's over. Now let's consider other possibilities to be able to compute this integral explicitly. So let us make a substitution z equals to x to the power n. Of course, you can ask why we can do it, but okay, we just see. So it means x is z to the power 1 over n. You cannot write nth root because n is a rational. It may be not integer, and in fact, most interesting cases when it is not integer. So dx is 1 over n z to the power 1 over n minus 1 dz, right? And what we have after that? Look. So integral, okay, once again I use same sign, same connection for integral. So it gives z to the power m over n times az plus b power p times 1 over n z power 1 over n minus 1 dz. So, let me write explicitly power of 1 over n, z to the power m plus 1 over n minus 1 az plus b power p dz. Look, if we look at this integral, then the second case when we can compute the integral appears immediately. How? This is the case when m plus 1 over n is an integer. Because if that is an integer, right, so let's say m plus 1 over n equals to lambda, let's say, right? Then we can make a substitution az plus b equals to t. So, and what it gives? Let me continue to equality with two circles. 1 over n integral. Okay, maybe I should write immediately a dz equals to dt, right? So it is not a problem to replace dz by dt. That is not a big deal. Okay, so what remains? Let me write. So also z equals to t minus b over a. So we have t minus b over a power lambda minus 1 times t to the power p and also dz is dt over a. Now look, what is it? P is a rational number, right? But lambda is integer. Lambda is integer. So this expression is a rational function. It means that now we have rational function of t and how to say, okay, I'll write nu of t dt, where nu is denominator of p. So p is, okay, something like s over nu, right? So we know how to compute this. Namely, we should represent t to the power nu equals to new variable s. Of course, now there are so many substitutions, right? Altogether, one, then other. Let me write what we have at the very end. So, look, t was this one, z was x to the power n. So I can write all together a x to the power n plus b power nu equals to s. And that is the substitution. So, for this integral, I refer to the first part of our section today, right? We know that this substitution transforms that integral into an integral of a rational function of t. Of s, rational function of s. So it means, look, second case, when we have m plus 1 over n is an integer, then the substitution is the following. So we should represent ax to the power n plus b power denominator of this p as a new variable. And there is a third case when we can do it. And, okay, how to do it faster? What I did? Yeah, so yeah. Third case, we can obtain in the following manner. Look where we stopped before second case. We obtained that expression, right? And how we could compute it? We could compute it when this exponent was integer, right? Now, the idea is the following. So, look. We had a linear polynomial, right, of z. Now, let us transform it a little bit. Instead of z, take 1 over z. Right? So, it means let's replace z equals to 1 over w, let's say, right? Make such a substitution. Then what happens? Once again, what is dz minus dw over w squared? So we substitute everything from this point. 1 over n integral of w power, I put minus m plus 1 over n plus 1 times a plus b w power p w power minus p minus here and dw over w squared. Look, this is very similar to what was written before, m plus 1 over p plus p minus 1 a plus bw power p dw. So what we have here now, look, compare this with what we have at that point. It's very similar, right? So we were able to compute this integral for the case when this ratio is integer, right? So it means now we will be able to do it when this expression is an integer. And that is the third case. The third case, m plus 1 over n plus p is an integer. And we know what to do then. Look, I'll repeat what was written. Firstly, a plus bw is t, right? First substitution was here. Now, instead of az plus b, we have a plus bw, right? So a plus bw is t. And then t to the power s equal t to the power nu equals to s, where nu is again denominator of p, right? And now let us collect everything together back. What is it? What it gives to us? Okay, maybe, where is it? W is here, right? So A in fact, that is not very good. Z was x to the power n, so a plus b over x to the power n equals to power nu equals to s, right? That is the substitution. And this is not very convenient, in fact. This is not very convenient. So, no, it's okay, yeah. That is precisely, yeah. So, quite often it is written like that is the substitution, So, let me review everything what we did up to now. Look, we want to understand when we are able to integrate this expression, right? The first case was when p is integer, right? It was the first. Second case, m plus 1 over n is an integer. Then the substitution is ax to the power n plus b power nu is s, where nu is denominator of p. The third case when m plus 1 over n plus p is an integer. Here the substitution is a plus bx power minus n power nu equals to s, where nu is the same as in the second case. And it turns out that no more possibilities to find a primitive of this expression. No more possibilities exist. And that is Chebyshev theorem, Chebyshev theorem, Chebyshev. The integral x to the power m ax to the power n plus b power p dx m n p rational a b real, the integral can be expressed with the help of elementary functions, if and only if one of the following three relations hold. So first, let me collect them once again. P is integer. Okay, here we represent x to the power lambda equals to z. Lambda is a common denominator of mn. Second case, m plus 1 over n is integer. Here ax power n plus b equals to no. How I wrote okay, power I wrote nu, right? Nu here. Nu equals to, let's say, s, where nu is a denominator, the denominator of p. And the last case, third one, m plus 1 plus p is integer, then a plus b x to the power minus n power nu equals to s with the same nu, right? Nu is the same as in 2. So no more cases. That's most important. W squared and w to the power of minus p. W squared is here. I'm sorry, I didn't look. It was w plus 1 divided by w squared, gives w minus 1. W minus p is over there. It is written. W to the power of minus p did not disappear. Okay? Okay. So, yeah. You see, it was not so complicated to be able to compute the integral in those cases. But of course, it's another essentially more complicated story to prove that no more possibilities to find that integral. In all other cases, you are not able to compute that integral in terms of elementary functions. In principle, it's impossible. That is the result of this theorem. Okay. How much time we have? We have just 1 or 2 minutes, right? Yeah, I think it makes maybe just a few words about in fact, a few words about the science in principle. In fact, this problem to decide when you are able to express an integral with the help of elementary functions, that problem was in the center of mathematics during 19th century. And I would say that many modern branches of mathematics were born because of this. They appeared. For example, algebraic geometry appeared when, I would say, with Abel's theorem, which can be formulated easily even now. In fact, I don't want to spend just 1 minute, because 1 minute is not enough to write down even the formulation for that theorem, but in Russian I gave even proof of that Abel theorem, so it is not very complicated, but it gave a start to many investigations. Because of them, algebraic geometry appeared. And up to now, it is quite important for so-called symbolic computations. So symbolic computations, they use a possibility to express integrals in terms of some given elementary functions. So still, don't think that if you have a computer, you are able to compute everything. It's almost true, I would say. But still there are unsolved problems. Okay, thanks for your attention.